This is a video that's related to section 13.7, and we're talking about tangent planes in this video. And specifically, we're talking about tangent planes to a given explicit surface z is equal to f of xy at some given point of interest x naught, y naught. So that would be the extra information that you could attach to the tangent planes word. We're trying to find a tangent plane to some surface z is equal to f of x and y. This is given. And you've been given a particular point of interest x naught, y naught. And here's your point on your surface. And we are trying to come up with this thing right here, this idea of the tangent plane. And this is the plane that is best approximating the surface at the point x naught, y naught. So we're trying to come up with this plane idea. This tangent plane right here, the tangent plane, this is the Calc 3 equivalent. The Calc 3 equivalent of the tangent lines idea. Tangent lines idea from Calc 1. Okay? So, you should know at this point, and you should be very familiar at this point with computing the curves on the surface. You should be familiar with the curve on the surface in the x direction, the curve on the surface in the y direction, and their associated tangent lines, Lx of t and Ly of t. Okay, so in the picture, you've computed the curve on the surface in the x direction. This is our Cx of t. You've computed a curve on the surface in the y direction. That's your Cy of t. And we have computed the tangent lines to each of those curves. Okay. So this is the prerequisite. This is what you need to know. You need to be able to compute these tangent lines in these x and y directions. And if you can do that, that's the first step towards computing the tangent plane. So let me do a quick example, just making sure that you're up to speed here. If you need a more detailed example, then look at the prior videos from section 13.3. Okay, so x squared plus y squared. We've got a point x naught, y naught. This is a point that's been given to you, and it's, say, let me change it to the point, yeah, here we go, the point 1, 2. Okay, 1, 2. Okay, and we want to compute the curve in the x direction. Okay, now what is this? In the x direction, and it goes to the point x naught, y naught, it will be 1 plus t, comma 2, and then your curve is 1 plus t squared plus 2 squared. There is your curve in the x direction. Your curve in the y direction, okay, it'll be, goes to the point 1, 2 plus t, 2 plus t, and then you'll get 1 squared plus 2 plus t squared. So there are your curves in the x and y direction. Okay, if you compute them out, you can see the answers right here. Cx of t, if you expand it out, you should get 1 plus t. You should get this function here, expand it out. Okay, the idea behind the tangent line in the x direction. Remember that it's a point plus a direction vector times t. So the point that your tangent line goes through is x naught, y naught, f of x naught, y naught, plus your direction vector times t. Well, since it's the tangent line in the x direction, your line will point in the 1, 0 direction, and what goes here in this spot should be your partial derivative f sub x evaluated at x naught, y naught. Okay. So if you compute this out, you will get the answer 1 plus t, 2, 5 plus 2t. Okay, that's what you will get. I think you can see here that the point is 1, comma 2, comma 5, plus the direction vector, number in front of the t, 1. The number in front of the t here is 0. The number in front of the t here is 2. So that is the equation that's the form of a line. Okay. So what this is the direction vector for the tangent line in the x direction. It's 1, comma 0, comma 2. Okay. If I wrote that out, it would be 1, comma 0. It would be the partial derivative of f in the x direction evaluated at x naught, y naught. That's what would go there. Okay. The tangent line in the y direction. Okay, it'll be a point plus a direction vector times t. Again, it'll be of the form x naught, y naught, z naught, f of x naught, y naught. The z value is just the function evaluate the two x, y points. Plus the direction vector should be 0, comma 1 times t. And what goes in this spot is the partial derivative of f with respect to y evaluated at x naught, y naught. So if you compute that out for this problem, right, you will see that the line in the y direction, 1, comma 2 plus t, comma 5 plus 4t. Okay. I think you can see that this is of the form 1, comma 2, comma 5. Oh, this should be a 5 here. 1, 2, 5. Right? 1, 2, 5. I was looking at the wrong function. And then the direction vector is 1, 0, and then we get a 2 there. Okay, so that's fine. Plus the direction vector for the line in the y direction. Here's your line in the y direction. It's of the form 0. There's no t here. The number in front of the t in the y entry is 1. The number in front of the t here is 4. Okay. So what we're saying here, the direction vector for L sub y, the line, tangent line in the y direction, okay, is 0, 1, 4. And that's of the form 0, comma 1 because it's going in the y direction. And then this would be f sub y evaluated at x naught, y naught, the partial derivative of f with respect to y at the point x naught, y naught. Okay. So at this point we have two direction vectors. Okay. And if you need to see the exact plot, here's what it is for this function, right? The two black curves are your curve in the x. This is the curve in the y direction. There's the y direction. This curve is going in the y direction. The one going this way from left to right is the x direction. That's the curve in the x direction. And then the red lines are the tangent line, this one right here, tangent line in the x direction. This is L sub x. This here curve, tangent line in the y direction. This is L sub y. Okay. So if I were to just do a sketch of that, okay, curve in the x direction, curve in the y direction. Let me just draw my axes down here, x and y. So here's c sub x. This would be c sub y. And you've got tangent lines at these points. Okay. The direction vector for that tangent line, okay, 0, 1, partial derivative of f with respect to y. The direction vector for this line, 1, 0, f sub x. Okay? And our goal is to find this tangent plane. That's what we want to find. That's our goal. Okay? Okay. So, what do you need to find the equation of any plane? Any plane. Isn't it of the form y is equal to n1 times x minus x naught plus n2 y minus y naught plus n3 z minus z naught. And in this case, our z naught value right here is just going to be the function evaluated at x naught, y naught. Okay? So you have your point on your surface. This is your point that you want your plane, point that the plane goes through. The point that the plane goes through. There's your point x naught, y naught, f of x naught, y naught. Okay. What we need to find is the normal vector, n, n1, n2, n3. What is this going to be? Well, it's the normal vector. There's n. And we have two vectors that we know are in the plane, and we want to find the vector that is perpendicular to both of them. So n, or n1, n2, n3, should just be the cross product of 1, 0, f sub x, cross product with 0, 1, f sub y. These were your direction vectors for your two lines. They are in that plane. So cross product them together, and you will have your normal vector. And if you have your normal vector, you will then have able to fill in the equation of the plane. So let's cross product these two vectors together. Okay. I think you can see here that the I entry of this vector, it should be 1, 2, 3. The cross product of two vectors is itself a vector. The cross product will be, knock out the I and the j, and you will get minus f sub x. Okay. Okay. Remember, the j entry gets an artificial minus sign, so when you knock out the j entry, you will get the doing the determinant here 1 fx, you'll get an f sub x here. And in the k entry, you'll have a 1 times 1, 0 times 0, you'll get a 1. Okay. So my claim is that this is your cross product of your two vectors that are in the plane. We just got those from the direction vectors for our line, tangent lines. Cross them, and you now have your n1. n1 is negative f sub x. n2 is negative f sub y, and n3 is equal to 1. So putting these together, this tells us that our tangent plane to the function z is equal to f of x and y at a point x naught, y naught is, okay, of the form negative f sub x, the partial derivative evaluated at x naught, y naught, there is your n1, multiplied by x minus x naught, minus the n2, f sub y, evaluated at x naught, y naught, times y minus y naught, plus 1 times z minus f of x naught, y naught. There's your z naught entry. Set that equal to 0, and there is the equation of your tangent plane. Okay. So pretty quick example here. Z is equal to x squared plus y squared. Let's say your point of interest is x naught, y naught is 1, 2. X squared plus y squared is your f sub x, f of x and y. So the partial derivative of f with respect to x is 2x. The partial of f with respect to y is 2y. And therefore, our partial derivatives evaluated at x naught, y naught is 4. Is 2, which is the same thing as 2 times 1. Here's your x naught entry. The partial derivative of f with respect to y, f of x naught, y naught, is 2 times 2, which will give you 4. So now I know that the equation of this tangent plane, let's see, I do know the normal for this tangent plane now. It was minus f sub x, minus f sub y, comma 1. Okay, so our normal vector is negative 1, negative 4, 1. There's the normal vector for your plane. And you know the point that it goes through, x naught, y naught, f of x naught, y naught. You know that it is going to be the point 1, 2, 1 squared plus 2 squared. So you know that this plane should go to the point 1, 2, 5. and have this as its normal vector. So now you can write down the tangent plane 2x squared plus y squared at the point x naught, y naught is equal to 1, 2. Okay, you would write negative 1 times x minus 1 plus 2, minus 4 times y minus 2, looking at the x, y naught point, and then my z entry of the normal vector is 1 times z minus 5 equal to 0. There is your tangent plane in implicit form. And if you were to just solve for z, if you solve this for z, if you just solve that for z, what would you get? I would add 5 to both sides. I would move these 1's to the other side, so you would get 1 times x minus 1 plus 4 times y minus 2. Okay, and here you would have the explicit form of your tangent plane. Okay, so this one you would plot with contour plot 3D, or this one you could plot with plot 3D because it's explicit. So the second form of our tangent plane to z is equal to f of x and y at x naught, y naught, you have two possible ways to write it. One, you can write it as the implicit form of the tangent plane, in which case you would write it as negative f sub x evaluated x naught, y naught, x minus x naught, minus f sub y evaluated x naught, y naught, y minus y naught, plus 1 times z minus f of x naught, y naught. That is the implicit form of your plane, tangent plane. The second way you could write it is explicitly. And explicitly, I would just write, I prefer to write the tangent plane as a function of two variables, L of x, y. The tangent plane explicit would be your function evaluated at x naught, y naught. That's the 5 here. That's your function evaluated at x naught, y naught. Plus your partial derivative evaluated at x naught, y naught with a plus sign. X minus x naught, that's what we were seeing here. And then you could add on one more piece, plus f sub y, evaluated at x naught, y naught, y minus y naught. So there's the explicit form of your tangent plane. Okay. Scrolling down in the Mathematica demos, I think there's this nice little tangent plane demo here. Let's see, you would just put in the function that you wanted, your x naught and y naught values, and run it. And here you can see that if we expanded this out, right, the computer is showing us the expanded form of it. In blue, I'm sorry, the clear gray, that is your surface, that is your function. Here we are at the point x naught is equal to 1, y is equal to 2. So right here is where we're drawing our tangent plane at, and the plane is given in as the blue curve, and it is given in a simplified form as for the function above is 2x plus 4y minus 5. Okay. And I think if you expand this out, that's what you will get. You can see the x plus 4y, x naught, y naught. Here you run this. My concern here is I got a 2 in front of it. But my, and then a 4. Yeah, let me rerun this code to make sure I'm getting the right plot here. Okay, so our function is x squared plus y squared. We're at the point x naught, y naught. Our partial derivative is 2x. Partial with respect to y is 2x. Okay, and yeah, did I write the wrong normal vector here? Oh, 2 times 1 is 2. This should be a minus 2. This should be a minus 2, and this should be a positive 2. Okay. All right, so I think that you can see when you expand this out, when you expand this equation out, you'll get 2x plus 4y, and then you'll get 5 minus 2 minus 8, and that will give you a negative 5. Okay? So the point that I'm trying to make here is that this tangent plane is a function, L of xy is a function that pretty well approximates this surface here. And that's the idea behind the tangent plane. It is a good approximation to your function. If you put any other point here, pick your same function, change the point x naught, y naught, rerun the code. There, you have your function, but at a different value, and the blue plane is, a good approximation. You can see it matching up pretty well. So that would be something that you could try now if you had a function f of x and y to be x squared plus y squared, and all you did was change the point x naught, y naught to be 3 and negative 1. Could you show me that the tangent plane, I'll leave you to fill in details, that the answer you'll get is 6x minus 2y minus 10. So that's what you should show. Okay. And the same process will work for any function. Z is equal to f of x and y. You want to find the tangent plane at x naught, y naught. Use these two formulas, whichever one you like the best. And the one you like the best probably will depend on which way you'd want to plot that function. Okay. So I think you can merge these two demos together. Here's the one for the tangent plane. Here's the problem up here where we have computed the lines on the surface in the two directions. You should be able to put a tangent plane on this plot. Okay, you have enough to do that code. And that's what the subject of probably your next assignment will be.